What's up, everybody? Welcome to Minerals. Let's finish up this segment of class and move on. So I'll go back first to an igneous rock, granites, that we've already talked about. At that point, we said this rock is made up of a whole bunch of different minerals. Granite is an easy one to spot them. You can see there's pink bits, there's white bits, there's black bits, and so on. Each one of those being its own mineral that out of that magma formed got larger and larger and larger, right? So now what about the minerals themselves? How do we work those, identify those, figure those out, distinguish them from their mates? And in like what circumstances? So here's ridiculously big crystals of gypsum from the front page here of this chapter of your text. You know, in what environments would you find that versus one where you can't necessarily pick one out to do some of these tests on versus like say a sandstone where they're all fine bits. They're still made of minerals, but not like recognizable in their crystal form. They're all the building blocks of rocks. They're all part of the rock cycle. But in certain cases, maybe minerals are easier to identify if you have the actual bit, right? Like, where's my quartz? So there's a nice quartz crystal, and there's some of that in here, right? But not as this nice crystalline form. So what we'll look at for most of this chapter is just going to be how do you do those tests that would show you which ones are which. With the good news, well, hopefully good news for you, is that we're skipping like a whole bunch of this unit. All this chemistry stuff, we're pretty much going to let slide by, stick to the basics. So what is a mineral? The definition I always use is a naturally occurring inorganic solid. So your textbook skips the inorganic parts, but mentions it here, that it can't be made by humans. It really can't be made by any life processes. Made of specific elements and arranged in a particular repeating three-dimensional structure. That's pretty much the way that I would say it if I was doing this. That you got to have, and again, we won't worry about the chemistry specifically, but that you got to have some sort of crystal lattice for it to count. Back when we talked about volcanic glass, we mentioned maybe that's one of the reasons why that would not be considered a mineral, because it cools so quickly it doesn't have time to form this. It cools so quickly that it doesn't necessarily even form minerals. It forms that amorphous glass. That's what we mean by this arranged in a particular three-dimensional structure, is that mineral pattern repeats. And in fact, the repetition of that pattern is what makes it what it is. Classic simple mineral in every lab: salt, rock salt, halite. And in every lab except for mine. I don't have a piece of it in this box. If I did, it's a cube. If you break it, it's a smaller cube. If you find a bigger chunk, it's a bigger cube. And the reason why it is because the sodiums and the chlorines that make it up like to attach to each other chemically in a tiny cube. They always do that, 90 directions in all three dimensions, right? So do that over and over and over and over again. You end up with a larger cube. The quartz that I had is a tetrahedra shape, which I'd imagine is in here somewhere. Again, we won't panic about. Look at all that. We're not going to do that. All right, maybe it's not, but like a little pyramid with a pyramid bottom instead of a square bottom. Repeat those over and over and over again, and you can get that kind of shape as you go up. So what are we going to do? Let's talk about the, there you go. There's your tetrahedra. Let's talk about the test specifically that we would do. Should we all be together in a mineral lab? What are the tools, the things you have to distinguish which minerals are which? Understanding that you're taking this class online and that you're not going to be able to like take one of these plates and do these streak tests on a test, right? It's just not going to happen. But what I suppose I could ask are questions that would like deal with what these different tests are, how they distinguish properties, and we'll check it out. So read your book with these sections, listen to this little hopefully quick video, and we'll see how it goes. So color. Interesting they put it first, because honestly, it's maybe one of the least useful tests for minerals. Yes, some are giveaways. If I were to hand out this box, even people that don't have a ton of experience can pick out the sulfur pretty quickly. It's got this pale yellow color, which isn't showing up great in this light, but this pale yellow color to it, which is unique. Great, but there's also like tons and tons of minerals that are like clearish, whitish. Lots of them that are like dark grayish, blackish. So if I gave you a whole tray of those, I could give you a whole bunch of different whitish ones, in which case color doesn't do you anything. Simultaneously, there's some minerals that exhibit multiple colors. So that's not going to do a whole lot of good to say, like, oh, this one is clear, this one's purple, this one's pink, this one's got kind of a smoky color. Those could all be quartz. So color doesn't do anything for you in that context either. So it's like borderline useless, except for like the special scenarios where it is a bit of a giveaway. More valuable, and what sometimes feels weird because, let me find a good one to do this with, because I guess when you're a rookie, it feels like I'm saying the same thing here. Like this feels like color as well, but this is called streak. You have these unglazed porcelain plates. They're finely porous. If you take a mineral and scrape it on there, it leaves behind a powdered form of the mineral. And believe it or not, although it sounds like color, that's a better diagnostic property for identifying minerals than color is on its own. Check it out. And hematite does leave a good one. And there should be one in this box, but there's not, so we won't worry about it. Right there you go. There's a better than I can do on my camera anyway. That reddish brown streak is like an easy giveaway for identifying hematites. And it's really the trick. If we were to do this in a lab setting, it's really the trick is some tests for some minerals are great, some tests for other minerals aren't so great. And it's thinking through it, figuring, using your head, and putting it all together to figure out which ones are which. Also great is luster. So luster, first sentence here, perfect. The way that a mineral reflects light. It's not color. It's not clarity. It's when light hits it and bounces off of it, what do you see in your eye? So take that quartz that I had. I can like see through it a little bit, but that's not what we're talking about here. If I go like this and I shine it in the light, what do I see bouncing off of that? Broadly, the big categories are whether it's metallic or non-metallic. This, even on this not so hot camera, looks like a lump of metal. The way that it shines, the way that it's not metal, but the way that it shines and reflects light looks metallic, right? That's different than shiny. Here's a piece of mica. It also shines like that other one did, but not in a metallic way. In fact, it's a little bit transparent. Again, not that transparent is a luster, but how does it reflect its light? And there's all kinds of ways to describe it. Again, metallic, non-metallic is like the big start there. From there, glassy, earthy, silky, pearly, resinous. There's like different ways to say it. But again, since you're not going to have a box of minerals, let's just kind of recognize the broad categories and be happy with that. Hardness is a fantastic one. The Mohs hardness scale, MOHS, that's this guy's name. That figured this all out. It's ignore the y-axis here for a minute. Let's just say it's a scale from 1 to 10, and they're not anything. They're not units. It's not 6 somethings of hardness. It's 6 on a relative scale, saying that these minerals above it are harder and these minerals below it are softer. With the idea being, if you take a harder one and a softer one, these two are dramatically different. The harder one should scratch the softer one. There's other tools you can use, like your fingernail falls right at about 2.5. So this one's softer than that. This, in fact, is talc. This is number 1. I can scratch it without problem because my fingernail at 2.5 is harder than that mineral. So like right away, again, if you combine a couple of these tests, if you were to get its luster, its streak, and now we know that it's very soft, you're getting closer and closer to identifying what that mineral is. Glass is often used too. This is quartz. It should scratch glass. And I don't know if you can hear it or not. Nobody likes that sound anyway, but it leaves a scratch in the glass. So it's harder than glass. Now, I won't ask any numerical questions with this, like measured hardness idea. If you go and calculate that, we see that it's not like this 1 through 10, again, isn't anything. It's a relative scale. Then how hard it is according to like testing. It's not even like a super smooth curve, and it's an okay curve, but all we'll do is the Mohs deal. This one's harder than this one, and so on, numerically. 10's the hardest, 1's the softest. Cleavage and fracture, let's go right to that, is going to be, and this can be based on what the mineral is made out of like chemically how the atoms grab each other as they build more and more and more bonds. Basically, it breaks down to, let's find some good cleavage ones like this one. When it breaks, does it tend to break along predefined planes within the rock? See how that looks like a parallelogram? Within the mineral, I apologize. See how that looks like a parallelogram? This is broken off of a larger piece, right? If I took a hammer and banged into this, I would end up with smaller parallelograms because this rock exhibits cleavage. It likes to always break along those predefined planes. Maybe harder to see, but a thing. If you can see lots of parallel faces, it's going to be your hint that we're talking cleavage. If it just kind of looks like a banged up rock, nothing repeats itself there, nothing's flat, I don't see any parallel lines. Sorry, I still got a scratchy throat here. So that would be what we say is fracture. This is like an either or. Does this exhibit cleavage or fracture? The micas are neat examples of cleavage. They have cleavage in one direction in like flexible thin sheets. So you can do it. I mean, I could like peel this. Look how thin it is. I could peel it and get a really thin layer off there. It likes to break along those. And again, they mentioned it up here in this like chemistry section that we're going to ignore. It's a sheet silicate. So the way that the quartz tetrahedra like to grab each other, the silica tetrahedra, is like side to side and they go out, 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 out. But they're not super good at grabbing onto each other in stacks. So the out is strong, but the layers on top of each other are weak, which is why you can cleave it apart in that direction easily. All right. Excuse me. Let me just blow my nose. All right, which leaves us with density. Again, you're not going to have equipment to measure that at all, right? But conceptually, let's understand it that if I were to hand you this, there'd be no doubt that you would say, like, whoa, that's heavy. Like, for this size, it feels kind of hefty versus this one feels pretty light, right? Now, yes, with a test tube and a trouble beam balance, we can measure the density fairly easily. But due to the stuff that's in it, it's another diagnostic property. Does it feel dense or not? Then the other properties are kind of the the ones that don't necessarily, like you wouldn't start with these. They're the ones that if you do it, it's a dead giveaway. It makes it easy. Like there's one that's magnetic. Yes, this is right here. Magnetite is strongly magnetic. So you do that and it's like, boom, I got magnetite, right? Calcite bubbles in acid. Halite, salt, surprisingly, tastes salty. Talc feels kind of soapy, I guess. I've always heard it as kind of like a greasy feel to it. So they're like the unique giveaway properties that maybe aren't like relevant to all of the tests. You wouldn't like grab a box and lick every one to see which one is salty, right? But it could be the last giveaway you get to figure out exactly which one it is. All right. So that said, again, chapter summary, we blew by most of the chemistry stuff, and I'm going to be okay with that. So the properties and the idea of them being the building blocks of rocks, and I think we'll be good to go to wrap up this unit and move on to where we're going next. So test coming up. Thanks, everybody. Good luck on it. We'll talk to you soon.